And I have some P1, some P here, P1, some P2 here. I want to connect this point to that point, okay? So here is my solution, for example. So this integral is along that line, okay? And you can easily show, so actually this is P1 and P2, right? It's no longer over time. You can easily show that this is actually twice the area between this curve and the line connecting the 2 points. So if this area is A, this integral is 2A. Okay? You can go and check that. I mean, it's easier. Any questions so far? So in three dimensions, you can do the following. So this is Q1, Q2, and Q3. So in the plane I have P1 here, I have P2 there. Here is my excursion in the plane. So, but during that excursion I gained this distance actually. So this is the red line is the three-dimensional excursion. The black is the projection on the Q1, Q2 plane. So this is the line in the plane connecting the 2 points. This area is A. So actually this vertical distance that I gained along the Q3 axis is 2A. Okay? Any question about that? Any question?
Professor, you said A is the area, right?
Yes.
But from P2 to, and that vertical distance is length.
Yeah, that's right. So we're saying, I mean, we're not caring about units here. These are unitless. It's not. We're saying geometrically, you can prove that this is actually the area between this curve and these 2 points. Okay. You can show it mathematically. It will not take more than 2 lines. Any questions so far? So we already know that I can go from any P1 to P2 in that plane because I have direct control authority on Q1 and Q2. But the issue is that while doing that, can I achieve any arbitrary Q3 final? And you can see it from here. It's as if, okay, someone is asking you, I want to reach Q3 final 10 units. So this means connecting these 2 points here with a curve that has an enclosed area of 5, right? Somebody else wants to do it with to reach 40. So now we're asking you to do it and enclose an area of 20, right? So the question of controllability now boils down to the question of connecting 2 points in the plane with an arbitrary area. Can you do it or not? If I give you any area, can you do it or not? Yes, because I can go all the way here and come back, right? And give you whatever area I like. And this is actually signed area. I can go the other way around to get a negative A. Okay? So the controllability question here is actually a pure geometric question. The proof here is easy. Okay, so we proved already that we can reach any Q1, Q2, Q3 in the plane using geometry or using differential geometry by the log, right? We have the log, we have 3 vectors, G1, G2, and the E bracket. So this is a very generic proof, or for this very simple example, we can do it via geometry, no differential here. Having proved controllability, you need to do the steering. So let's do the steering. Here is my system, Q1 dot is U1, Q2 dot is U2, Q3 dot is Q1 U2 minus Q2 U1. And here is the problem that Brockett formulated. Find U star of t, that steers, which is a very natural problem to formulate, to write down. Steers some Q naught to some Q final in t final say equals 1 second. Don't care about time now, it's an unbounded control problem anyway, we can do it in whatever time you like, if I can do it in 1 second. Find U star that steers Q, some Q naught given some Q final given in 1 second and minimizes J 0 to 1 the control energy. What type of problem is that? What do you call this problem?
Optimal control.
Optimal control problem. Very good. So how do you solve it? On triagonal maximum principle. But we didn't take here in this course optimal control. I will not rely on some of you taking optimal control. I will rely only on the tools that are stated in 241 and here. Okay? So let's reformulate this problem. And actually this is what Brockett did also. He didn't do it using Contreras. But of course we can. This is a typical optimal control problem. So this problem is equivalent to the following problem. I will get rid of U, the control inputs, completely, because whenever I have U1, I can substitute it for Q1 dot. Whenever I have U2, I can substitute for Q2 dot. I can get rid of controls completely. So I will just I'll try to find the trajectory, the optimal trajectory. The solution of the optimal control problem gives you both simultaneously, U star and the optimal trajectory. But because U is nothing but the velocities, I can get rid of it and focus on the trajectory. Now it's no longer an optimal control problem. Let's look at that. Let's create an equivalent problem. So find Q star that connects the same 2 points, trying to create an equivalent problem. Okay? So this is now in the QT space. So from 0 Q naught to time 1 and Q final. So in the QT space, it looks like this. This is time, this is Q, of course it's an array. At time 0 it's Q naught, at time 1 it's Q final. And I need to connect these 2 points, please. Like this, like that. Obviously I have too many trajectories, so we want to minimize the same J here. What was the J? It was U1 square plus U2 square. U1 is Q1 dot, U2 is Q2 dot. So this is some function of Q and Q dot, right? So the question now, do you see that these 2 problems equivalent? But there is something more to be done.
Constraint probably.
What's the constraint?
The dynamics Q3 dot must be.
Very good. Why? Because, okay, I'm connecting the 2 points, I'm maintaining the same J, but I need to satisfy these equations. The first 2 equations are naturally satisfied because I replaced every U1 by Q1 dot. But the third equation remains without satisfaction, so I need to add subject to this constraint. I will make it 0 side. So Q3 dot minus Q1 Q2 dot plus Q2 Q1 dot this is sum psi of Q1 Q dot. This is 0. Okay? Any question about that? Any question, please? And what type of problem is this? What type of problem is this? What?
Isoperimetric problem.
Optimization.
It's calculus operation problem.
Yeah, it's a calculus operations problem. It's not isoperimetric, but it's calculus operations problem, right? Yeah, we need to connect 2 points and minimize some functional subject to some constraint. The constraint is not an integral constraint. This is why it's not an isoperimetric.
But we
It's
can,
what we call finite constraint.
we can put it in the integral form.
No, because it's for every single time. This is for all time. This is like infinite number of constraints. And we handled this actually in our calculus operations in 241. How do you solve this problem? Anybody remembers? How do you solve this problem?
First variation is equal to 0.
First variation of what?
First, form the augmented.
I need to form a Lagrangian because I have a constraint. And Lagrangian was f plus lambda times your constraint. The Lagrange multiplier now is function of time, it's not constant anymore because this has to be valid for all times. So it's like an infinite number of constraints. This is what we call finite constraints in 241, if you remember. Okay, so this is my Lagrangian. So here is f, q1 dot square, q2 dot square. For those of you who didn't take 241, you can go and watch these videos on calculus operations, or if you have any background calculus operations, just review it. Plus my lambda times the constraint. Okay? And then I form my Lagrangian. What else do I need to do? What's the next step? After I form the Lagrangian, do what?
Turn the crank.
Yeah, turn the crank. Lagrange equation, d by dt, partial L, partial Q, J dot, minus partial L, partial U, Q, J is 0 for all J, 1, 2, 3, right? If you do it for J equal 3, actually this gives you that lambda dot is 0, which means that lambda is a constant. That's a great simplification. So I got rid of this time dependence. Now J equals 1 is easy, with lambda is constant, gives you Q1 double dot plus, I guess, lambda times Q2 dot is 0, and J2 is the other way around. Q2 double dot minus lambda Q1 dot is 0, so you can lump them together into Q1 double dot Q2 double dot is equal to this matrix, 0, negative lambda, lambda 0, times Q1 dot Q2 dot. Remember, these guys are my control inputs, U1, U2, and these are their derivatives. This matrix, let's call it large lambda, and as you can see, it's a skew symmetric, little SO2, right? Skew symmetric matrix. So my equation governing